Welcome back, student. Let us see chapter number 4 as it is video number 18. Today's topic is Lorentz Force. Let us say in last video we have already seen Lorentz Force, but once again, as it is important, let us see what is Lorentz Force. Right? Lorentz force is given by F is the Lorentz force, and it is the algebraic sum of electric force, that is Fe, plus magnetic force Fm. Okay, electric force, when it produces when charge is steady, but when the charge is moving, then we will have magnetic force. So put the value of electric force and magnetic force, we will have equation, that is Q in bracket E plus V cross B. Right? So this is the equation for a Lorentz force. Give it equation number 1. Now let us see our topic, which is there on page number 135, and the name of the topic is magnetic force on current carrying conductor. So from here you have to take equation of magnetic force only. Mind well, that we will see later on. So the name of the topic is magnetic force acting on current carrying conductor. Okay, for this let us see one small figure which is not given in our textbook, but for our conveniency we can see. So consider a conductor. This conductor having length L and area A. So conductor having length small l and area, that is capital A, and charges are moving with drift velocity V. Okay, and these charges are moving in presence of, if there is a magnetic force, so there will be a presence of magnetic field, and that magnetic field is given by B. So once again, as shown in figure, consider a conductor of length L and area A. In this conductor, electric charges are moving with velocity V in presence of magnetic field. So the magnetic force is given by, that is F is equal to Q V cross B. So this is the equation number 2, which is equation of magnetic force, and that magnetic force is due to a single charge, one charge only. But here inside the conductor there are how many charges? There are charges n, number of charges L multiplied by A, means these are the charges present in a conductor. Okay, so the total force acting on these charges is given by F is equal to, instead of Q, it is for a single charge, but we have number of charge, that is N L A multiplied by Q as it is, and rest of the equation same to same. But what but we have seen in chapter number 3, what we have seen, that is N number of charges multiplied by V velocity of that electric charge and charge, that is N Q V is nothing but J. What is J? J is nothing but current density. Okay, so here for our conveniency, there is a magnetic field and the charges are moving with velocity v under the effect of magnetic field. So we will take here Vd. What is Vd? Drift velocity. So here there also be Vd. So Nq Vd is known as J. So Nq Vd, instead of that write down J. So our equation becomes J LA as it is cross B. Again, but what? But what is J? According to the definition, electric current passing perpendicular to the unit area of a conductor. That is, right? Make a subject I. So I is equal to JA. So instead of JA, what is this? It is the equation of magnetic force, that is F. Instead of JA, you will say I, that is I multiplied by L cross B. So we will have the equation of magnetic force acting on a current carrying conductor. Give it equation number 3. Got it? So this equation we will use when the shape of conductor is straight. But if the conductor is of arbitrary shape means it is not straight, it having a random shape, then you have to take algebraic sum of, means equation number 3 is used for a straight conductor. But if the conductor having arbitrary shape, right, then suppose this type of shape of conductor is there, then you have to take small part of conductor, that small part having length dl, right? So you will have the equation F1 for first part is equal to electric current passing is I, right? So I will be as it is dl cross magnetic field is uniform. Same way, let us take another part having same length, that is dl. So it is F2 is equal to I dl cross B as it is for first part. So let us take dl1 and it is dl2. So If you want to find the total force F is equal to, then you have to do the algebraic sum of all small lengths. So it is algebraic sum of I multiply by dl cross b. Okay, so this is equation number 4, and which is used for a conductor having arbitrary shape. Okay, so this is about Lorentz force and magnetic force acting on a current carrying conductor. Okay, now we will see one small but very nice topic. It is there on page number 140. Okay, and the name of the topic is velocity selector. Let us see. Okay, this velocity selector topic is used, that velocity selector is used for what? It is used to measure the charge to mass ratio, and it was employed by J.J. Thomson in 1897. So this velocity selector method, this is a method which is employed by J.J. Thomson in 1897, and this method is used to measure. What to measure? This method is used to measure gyromagnetic ratio. What is gyromagnetic ratio? It is used to measure ratio of charge to mass, that is charge to mass, and this charge to mass ratio is known as gyromagnetic ratio, and it is symbolized as charge Q by M. It is also known as gyromagnetic ratio. Right? This word is not there in our textbook, but we have taken from the reference book. Okay, let us see what is velocity selector. Right? For that, consider that Lorentz equation. What was the Lorentz equation? Again, F is equal to Fe plus Fm, but now we are taking direct equation, Q in bracket E plus V cross B. Okay, now let us see the velocity of a charge moving in which axis? Along x-axis, means the charge Q is moving with velocity V in x direction. So instead of V, we have to take Vi. What is I? I is the unit vector along x direction. So, as shown in figure, we must have to remember that charge is moving along x direction. So, the magnetic field produced is along, suppose it is along z direction. So, it is the magnetic field which is along z direction. So, instead of B, you have to write what? B and along z direction, B unit vector K. And we know that electric field is perpendicular to that magnetic field. So, this is the electric field which is along y-axis. So, instead of that E, we have to write Ej. What is J? It is a unit vector along exact y-axis. So, the equation becomes F is equal to Q as it is. Instead of E instead of, that is Ej plus V cross B, that means Vi cross B K. Okay, so see the replacement. In our standard Lorentz equation, we have to put instead of E, Ej, instead of V, Vi, and instead of B, Bz. Got it? So, you will have the equation, that is, which equation? Q as it is. Okay, this is the force F. It is a Lorentz force, but here we have to take the magnetic force only, that is Fm. So our E term becomes 0. So it is also 0. Mind well, this thing is not there in our textbook. In our textbook, directly this equation is given, that is F is equal to Q in bracket Vi plus Bk. Okay? If you want to see, then you have to see page number 140, 4.4.1. There is a topic. Okay, but what is I cross K? In 11th standard, we have seen I cross K is nothing but minus J. So, you will have equation, that is Q V B, here I cross K. What is I cross K? Minus J. So, we will have equation F is equal to minus Q V B J. What does it mean? This force indicates that it is along negative y direction. So, from figure, we can see that F is towards downside and it is magnetic force, right? Here electric field is already there, so there is electric force also, that is Fe. To indicate this electric force, we have seen in starting, we have taken that term E. Okay, So from the figure you can see that electric force and magnetic force, that is from figure, what from figure, that is electric force and magnetic force are mutually opposite to each other, as well as they are having same magnitude. Means here magnetic force is same as electric force. Okay, what is the equation of magnetic force? That is Q V B. And what is the equation of electric force? That is Q E. Right? Q will cancel out, and from here you will get equation of V, means velocity V is equal to E by B. Got it? So this is the main equation, right? From this equation, if you will take, or if you will select the value of velocity, then charges are moving between electric field and magnetic field without any deflection, right? So this equation is used for what? To select. What to select? To select velocity of charge, that is Q. And by selecting the velocity of charge, this charge is moving between electric field and magnetic field. How they are moving? Without any deflection, right? Without any deflection. You can choose without any deflection if the charge is moving, and for that you have to take the value of V is equal to E by B, right? So by this way, this method is used to measure the ratio of charge and mass, and because of that equation is known as equation of velocity selector. Okay, just select the value of velocity of a charge, then charge is moving between electric field and magnetic field without any deflection. Okay, so this is the end of our topic. Again I am telling you, you must have to refer textbook, then videos, then again textbook, and you have to write the topic in your notebook. Thank you.